I graded most of homework 11 already. I thought that for once I'd actually get ahead of the curve. So I graded 3 assignments today, depending on when you submitted homework 11. I think there were a couple of people who were still working on it. Here's homework 12. Basically, repeat what we do in class today on some watershed. It doesn't matter which one, except that I'd like the watershed to be at least 1,000 acres in size. And the reason why is that I'm going to show you how to do subbasins today. And to do subbasins on a really tiny watershed would, I don't know, it maybe not work out well depending on the resolution of the soil map in the area that you're working with. And so, of course, you're free to create watershed models for anywhere you like, but for this assignment, it should be at least 1,000 acres and have at least 2 subbasins. Okay, today what we're going to do is automatically calculate curve numbers. Now that you've had to manually deal with the soil data and you've had to go to the table in the book and look up a soil type, you know, the Fair Woods soil, the Fair Woods land classification. We're going to kind of go over an automated way of doing curve numbers and then use curve numbers and the DEM data and everything to put together a HEC-1 model. One thing you're going to need to download from MU Online today is this CN table file. And so if you click on that, then it should download automatically. It's formatted as a .tbl, but really all it is just a text file. So if it automatically displays like it is right now, what we want to do is we want to download it. So I think you're going to have to right-click on where it says CN table, because sometimes it'll just display it if it's a simple text file. So save target as, and then I'm going to put that on my C-temp WMS. All right. So just a note about what it is we just downloaded. It doesn't know that's a text file. What we just downloaded is a file that I created a number of years ago when I was trying to work on a research project, and I looked at all of the land classifications I could find in the West Virginia watersheds I was developing, and I went into the literature. And so if you look at what this is, there's 4 numbers here, and they correspond to soil group A, B, C, and D. I'll give you a moment to pull that up if you haven't got it already. Yeah, you can open it in the notepad. It's just a dot. It's just really a text file. I should maybe rename it as a text file. So I think that this covers most of the land classifications in West Virginia that will come up under the National Land Cover Database. That is one of the data files that in WMS we can just click the download data button and it goes and gets it for us automatically. And so I like it when it goes and gets the data automatically. I like it a lot. You'll notice that some of these, it's the same curve number regardless of soil type. For instance, open water. I'm not sure why open water wouldn't be 100, but that's what the literature says is use 98. So in each one of these cases, I had a citation or a reference for what I thought would be the appropriate curve number, but I don't know that it would hold up in court necessarily, and I'm providing it with absolutely no warranty, as they say. So it's just for educational purposes, but I think it's right. What we're going to do is use WMS to read this file relative to land use and soil types. So that's where we're headed. So let's start up WMS, and the project area we're going to be working in is in Morgantown. And specifically, here's the watershed that we're going to do. Maybe you know Morgantown, it's alongside a river, and sometimes just to find the project areas, you can zoom in and just try and have the shape of the river covering that corner edge of the screen, because it's already going to be a pretty big watershed, 4,000 acres, and if we make it too big, then some of you will have topaz taking a long time to calculate. So we don't want to do that. Okay, let's start with the hydrologic modeling wizard. Create a project. I'm going to call this one Morgantown. Save it. Now the bounds of our project, we can bring up the locator tool. There it is. And tell it that we want to be zoomed into Morgantown. Now, this is too much data. If we download all this, it's going to be way too much DEM. So let's zoom in so that we've got the curvature of the river in the upper left here. So what we want is we want where the river jots out a little bit. So here's that river. I think we've even still got too much data. So if we zoom in one more, it's maybe too zoomed in, 0.6 miles. Yeah, a mile. That seems about right. Okay, so has everyone got about that same view? It doesn't have to be exact. What we're trying to go for is we're between the bend in the river here. Our watershed extends up that way. So that if you've got both of these rivers, I think it will be all right. Yeah, I think this will be fine. Okay, so click OK once you've got that, and you may need to click on WMS again to get the coordinates to show up once you do that. Sometimes it's a strange bug. I sometimes have to click on the icon again to bring up the wizard another time. All right, we're going to use the web services, but we're going to go get more than we usually do. In the past, all we've gotten was the DEM, the 10-meter DEM. But this time, we're also going to get National Land Cover Database, 30-meter resolution. And we're going to scroll down, and we're going to get some soil data. Let's get the Surgo soil data. Surgo is high-resolution soil data. StatsGo was the one that was kind of low resolution. And just as a point of reference on how low resolution StatsGo is, I looked at it earlier today, and in this big watershed of 4,000 acres, there would only be 2 soil types assigned if we went with that lower resolution StatsGo shapefile. But so that's why we're going to get Surgo is, it's a little bit more detailed. And so we just click download data from web, and this will probably take a couple minutes for it to go and get it, especially since we're all going to throttle it at the same time. Now here for get the DEM size, we're already zoomed in enough that it's asking, do we want it to interpolate the DEM data? And it's saying if it does interpolate, it's instead of every 10 meters, it's going to have them every 10.25 meters. I'm just going to have it do the default 10. That means go get the full resolution and don't interpolate. If we were zoomed out and getting a really wide area, what it's offering to do here is to reduce the amount of complexity in the mesh that describes your elevation model. But I mean, we're close enough to 10 anyways that we might as well just go for the straight stuff, not water it down at all. So it goes and gets that. A pretty good download speed for that one. Now it's asking the same thing for the land cover database. By default, it's 30 meters. And if we were zoomed on a really large area, then it might suggest an interpolation. But right now, it's offering the 30-meter resolution, which is as good as it can get. If we typed in 10, because the other one was at 10, it's not like it's going to improve the data. 30 meters is the resolution there. So we'll just get that. And I don't think it asks for the Surgo. The Surgo data is a series of shape files, and it'll get way more than we need. And I'm kind of curious, because we're right on a border here with the soil maps. Earlier today when I was working on this watershed, it went and got Pennsylvania, West Virginia, and Virginia, all 3 of them. But I think if you zoom in just tight enough, then our project area doesn't include Pennsylvania. So I'm curious to see if this time it's going to get Pennsylvania for me or not. Let's see. So I'm getting West Virginia. Looks like, yeah, maybe I'm getting a second West Virginia as well. All right. So we can close the wizard here, and let's explore what we've got. I'll wait a moment in case yours is still downloading. For once, we're not actually in a rush today. We can leisurely make our way through the activity. You got the data? Okay. You got an image in the background there too. That's good. Now, occasionally save your file. I don't think last week I had any of you complaining that WMS crashed on you, but WMS was crashing on me earlier today. So let's save, just so that when WMS crashes, we don't have to start from scratch. So if you toggle off and on this GIS data, you'll notice that we don't actually need 77, West Virginia 77. We could just toss that out. In fact, I'm going to right-click on it and delete it. I don't know why it downloaded. I guess it thought we were close enough to that area that we might. I'm going to delete it. Now, this is kind of a mess, right? You can't see anything, so you can switch it off if you need to, and it'll still be there. Switching it off isn't the same as deleting it. So, the data's still there, it's just not showing right now. So as per usual, I'm going to go back into the wizard, and I'm going to, let's see, we've already read the data. Now I want it to compute topaz. Now, your flow accumulation threshold may be different than this 12 acres. If it's 1 acre, then you're going to see nothing but blue. If it's 1,000,000 acres, then you may not see any flow accumulation cells. So, somewhere around 15 or 20 acres is probably fine. It doesn't really matter. Click topaz. Take a moment to get through that entire DEM, and finally say normal program termination. There it is. Crashed? Uh-oh. Already? At what point? What were you doing when it crashed? How did you make it crash? You're getting the soil data. All right. Well, had you saved your work, or you hadn't even got there yet? Well, you had to create the file name when you started the wizard, right? All right.
15 acres.
Yeah, I think 15 acres is good. Now, wait, go back. You need to click that download data from web button. It's odd that in a couple of cases there's a secondary button you have to click besides just the next to actually have it do the thing. And in your case, you're going to go get that data. Did you already check the project bounds to see if it remembered them? Yeah, okay, good. It usually does. Now go. Okay. That one, and LCD, and then also scroll down to get the Surgo. Yep. And then download it. Fingers crossed it doesn't crash. Land use 30. 30, yeah. It was just the elevation data that we wanted it to stick with 10 instead of accepting its offer to interpolate. All right, so you have the, good, you've got the soil data. You're right up with me. All right. All right, so now once you compute topaz, here's the stream that we want, this one. So we're going to drop the outlet right at the apex of this curve, right in here. So you see where the cursor is? We're going to plop an outlet there. Now you can go into the wizard to drop an outlet, or you can just switch over here to the drainage module, and then it brings up the tools for creating outlet. So I'm going to drop my outlet right there. And I kind of want to be close enough to the blue line that it knows it's on a flow accumulation cell. And then you can do the delineate basins wizard here. Okay. And it will delineate. So my current data is in meters, but what do I want to see the report in? Acres for area and distances for feet. So it internally is going to be working in SI units, but since it's customary to view in traditional units, it'll display those as I get on-screen reports, and it'll also paste all of that information over when we're setting up the watershed model. Down here it says it's doing the work. Okay, so about 4,500 acres. That'll vary depending on where you drop the outlet. You know, if you were doing this for real because you're placing a culvert, then you'd have latitude, longitude of the culvert, and you could just look at the coordinates down here on the bottom of the screen to make sure that, you know, you'd zoom in, make sure that you drop the outlet in exactly the right spot. Well, if your outlet's in the wrong place, then it won't delineate. Did you drop the outlet not on the blue? Oh. Oh, well, I mean, if they said, hey, let's put a culvert right here, you'd say, well, you know.
You were saying before that, like, sometimes this doesn't match up with the
Oh, well, what you sometimes have to do is just make a reasonable assumption, like, let's say the image is saying there's a road and the road is like here. You know, it'll have the same basic shape as the creek, and so you'll say, well, all right, I know that the culvert is at the lowest point of the sag on the road, and the road and the creek are next to each other, so I'll pick the lowest point of the sag on the creek. Because, yeah, occasionally there will be an offset of maybe 20 or 30 meters in a really large data set. But, you know, that 20 or 30 meters is kind of inconsequential when it comes to 4,000 acres. And it looks like a line like this is bad news. It means I have to redo my project area because this isn't the whole watershed. Did all you guys have the same problem, or some of you actually captured the entire watershed? You've got the whole thing. How about yours? Has yours done topaz yet? Yours just did normal program termination, right? All right. Huh? You were in a daze? Oh, it's thinking. All right. You got yours. He got his. I'm the only one who has to do it over again. That's the bad luck. All right. So I need to pan up a little bit. So I'm going to start over, throw it all out. It's an iterative process sometimes, figuring out where your project area, like the extents of your data. You don't know the extents of your data until you delineate a little bit. So if I pan down a little, I think I'm going to get that whole area that I need. I hope. This can get real tedious. All right, so I want to make sure I've got all three clicked, download the data from the web, 10. And then it'll download it, and then I'll say 30 for the next one. Okay. And then it won't ask for the soil data. It's getting it. When you start working at Pterodon, you can afford a new computer. Or maybe they'll give you one. If they do, make sure that you can install software on it.
Yeah. Don't want to be international.
All right, so I'm going to close this. And, well, no, I'll have it do topaz once it reads it in.
So how did you get rid of the previous topaz and stuff?
What do you mean?
Like you have to create the new one, so you deleted the outlet, and once you deleted the outlet.
Oh, no, I started a whole new project.
Oh, okay. So
Yeah. Mm-hmm. Yep. Because I didn't have the DEM data extents that I needed. I'm just hoping that I've got it now. I think your computer's faster than this one. And they spend $15,000 on these. What I'm standing behind right now, $15,000. And the computer can barely boot. Yeah. All right, so it computed Topaz. I'm going to switch these off so I can see. All right, so my spot of interest is right here on this sag, right? So I'm going to drop in the outlet there. Did it crash? All right, well, you may just be an observer tonight. Yeah. Hey, I got it. All right, just barely though. All right, so we've got our watershed. Does everyone have around 4,500, 4,600 acres? Okay, you've got it. Okay, so what we're going to do is explore this soil data. I'm going to throw out the one I don't need because this one's useless to me. Now, I want to explore this one though. And so here is a tool that is the identify tool. And if I want to find out what kind of soil is right by the outlet, right here in this outlet, I can click on that polygon, and what it'll pull up is it'll say this CWE is a key. And that may seem a little bit familiar based on the homework you had 2 weeks ago, remember, in the area of interest where Upshin, what was it? Upshur Gilpin is what it was. Gilpin Upshur. And so it had some abbreviation code. It was like a 3-letter abbreviation code. And so this is one of those. This is that same D, G, D. These are soil abbreviations. And so if we wanted, we could go onto the USDA website and find out all the characteristics of these kinds of soils. We could look up what's the minimum infiltration rate, what's the hydrologic soil group. Now there's hundreds of them inside of our watershed boundaries, and so obviously that's not what we're going to do. But just to let you know, there is data there. Now what we want to do next is, this is a tricky one, so watch carefully. Right click and then join NRCS data. Now when we downloaded that soil data, the way GIS data works is there's all these lines, and then there's table after table of supporting data. And right now, we don't have all of the data that we need associated with these polygons. And so when we click on Join NRCS data, what we're telling the computer is also look at those tables in addition to just the polygons themselves. And so now when I do that, it's asking some questions here. Okay, join the soil texture. I don't care so much about that, but I do really care about join hydrologic soil group. This is going to be critical for us to be able to automatically calculate the curve number. So we definitely want to join the hydrologic soil group. One other thing that's useful is fill blank values. It doesn't happen very often, but once in a while you'll have a watershed where the USDA data is missing for some small segment of your watershed. And what it can do is it can fill in the blanks with a default assumption. And so what it's saying is, okay, fill in the blank values, it's going to fill it in with C, soil group C. If you wanted to be even more conservative, you want to say, worst case scenario, I want it to assume D if we don't have any data. You could overwrite that. But I think the majority of this area is C, and so if anything is missing, most likely it's probably C. So I'm just going to stick with C. All right, for any blank values that have to be filled. So we click OK there. Now let's do that same thing again. Use this identify tool and click on a polygon, any polygon. And now the report is more extensive. Before it was just having this abbreviation, D, G, C. We didn't necessarily know what that meant, but there's a whole lot of additional data that it's joined from the table when we did that join NRCS data. So the most important for us tonight is the hydrologic soil group. So each one of these polygons we can click and find out what's the soil group. Most of them are C. There's a B, that's exciting. It's always exciting to find some good soil in West Virginia. It's rare. There's another one, B soil. All right, so we have our soil taken care of. I saw, as I was walking around, some of you have already been looking at the land use. It's kind of an interesting thing to pull up. It is it's a picture, and each color corresponds to a land use. So if we, okay, yeah, all right. So it only shows what you're zoomed in. If you click like this, then zoom out, it's almost looking like we don't have the data we need, but we do. So if you haven't already, let's add a map data just so we can get an idea of what we've got. So get online maps. I'm going to do the world street map. That's one of my favorites. And then we'll zoom in on like a border area that has some urban and some rural on this street map. And then we'll see if the land use kind of supports the difference that the street map is implying. Mm-hmm. Yeah. I think so, yeah. So if we go here to download data, you're saying like these, right? Yeah. Yeah, I think that it'll just add that in the same way that it got like the soil data. Yeah. Okay, so what I want to do is let's look at here on this screen. I want to turn off the soil data. It's getting a little overcomplicated. I can turn off the DEM contour lines for now. So all we're looking at right now is the drainage coverage, and in fact I could even turn that off. So what we've got visible right now is the only tag that's on is the street map. But I can turn on the land use and see how does that correspond to what we see on the street map. And it seems pretty accurate. Like this little subdivision here looks like this is a cluster of houses. You know, streets like these, that looks like these are houses here. And so you turn on the land use map, and sure enough, it's showing that that's an urban development that's separate from whatever this black is. And so that black color, it looks like this is undeveloped land. Now, unfortunately, I'm not aware of a way for us to click on these colors and have it automatically pop up the interpretation in the same way that we just did with the soil types. I mean, there may be a way, but I've just never gone to the trouble of figuring out how to, like the identify tool doesn't pop up in the same way. But my mind is at ease that it's reading things correctly. Number one, because I've used it enough times and it's given me reasonable curve numbers. But what I wanted to show you is that those different colors correspond to different land uses. What do you suppose the blue color indicates? Hey, exactly, it's water. We can tell because we know the curvature of the river in Morgantown. Okay, so things are matching up. What we're going to do now is calculate the curve number for our watershed. We can turn off the land use. We don't have to see it. Oh, cool, yeah. There it is. Paved area. Yeah, very good. I wonder if we zoom in. Does it have, is Cinnabon a different land use or cover type? Morgantown have a Cinnabon? All right. Okay, we don't necessarily need that world street map on anymore. Okay, we'll turn on the soil. We have to create a coverage. The drainage coverage is always there, but we need another coverage called a soil type coverage. And so up here, right-click on the word coverage, and we're going to do new coverage. So what we're doing is creating a place that data can be created, can be stored and read from. And so the coverage type we're going to do is a soil type coverage. Okay, so we want a soil type coverage, and we don't have to give it the elevation or anything else. We just tell it it's a soil type coverage, click OK, and now it's there. It's a soil type coverage. What we're going to do is we're going to move over the polygons in that GIS shape file and put them into the soil type coverage. Okay, so I'm going to turn on the DEM again, and I'm going to turn on the drainage so I can remember where is my watershed boundaries. Okay, there's the watershed boundaries. I want to make sure that I'm approximately zoomed in on the area of interest. So if you have your watershed there, all right, so now turn this on, and then here in the GIS module, what we're going to do is we're going to select shapes. So you see this cursor or arrow tool. We're going to select shapes, and what we're going to be doing is drawing a rectangle. It's a little hard to do because all you can see is these thick polygons for the soil type, but we want to, once we do this thing, we're going to click on one edge and drag so that the entirety of our watershed is inside the box we're about to draw. Okay, so I've got it turned back on, and I'm doing the Select Shapes tool. I'm clicking in one edge, and the entirety of my watershed should be in there. And so now it's selecting all of the polygons. And a lot, it's gone outside of that box that I just selected. Any polygon that's at least partly inside is going to be mapped to our new soil type coverage in what we're about to do. All we've done so far is we've said, okay, we want certain polygons to be selected right now, and then we're going to do mapping, and we're going to do shapes to feature objects. And so shapes to feature objects, we're going to map into the soil type coverage from this shape file. So next. Now the most important thing for us to map is the hydrologic soil group. So right now in this shape file, it has an attribute called Hydgroup, and we want WMS to interpret that as the SCS soil type. Now depending, if we were setting up other models, then we'd maybe want to know the KSAT, but for us it's just the hydrologic soil group that we want to make sure is mapped to that characteristics of Hydgroup. Is everybody with me? The selecting, the first couple of times, getting those selected can be a little bit weird. All right, it is the GIS tool, so the world, yep, the GIS module, and then it's that one, yep. And just click up there and drag down to the edge. Yep, all right, and then do mapping. Yep. Yep. Just next. And make sure that it's doing the Hydgroup to SCS soil type. All right. We're going to click next. I hate to keep you in suspense like that. It's a real cliffhanger. All right, next, and finish. And so what it's doing is if we turn off this soil data in the GIS, similar shapes have now appeared here in the soil type coverage, but only the shapes that were selected by our click and drag that we did. And the reason why it's so irregular, the reason why it's not the same shape as that box we drew is any one of these polygons that's at least partly in, the entirety of the polygon will be included in the selection. Okay, so now we have a soil type, and WMS knows for each one of those the hydrologic soil group. I think we could well, we've already seen the identify. Yeah, if you do the well, we won't bother. I thought we could look at the soil classifications again, but let's do the big finish. Let's actually calculate the curve numbers now for our watershed. We've got the land use specifying what's on the surface of the land. We've got the soil type saying the physical characteristics of the soil under the surface. And our watershed boundaries are defined by the DEM. You know, our drainage coverage is showing the watershed boundaries. I'm going to turn those off. They don't have to be shown. All right, so now go into the hydrologic modeling module. And if your drop-down box doesn't already say HEC1, change it to HEC1. And also, this would be a fantastic time to save, because what we're going to do next very well could crash your computer. Not that it's any great calculation, but computers crash a lot. Everybody save? All right. So what we're going to do now is this calculator and compute GIS attributes. And this is just a little dialog box here saying, all right, we're going to calculate the curve number based on the soil type coverage and based on the grid for land use. And if you look, the only thing we've got right now as our grid is the land use grid. So that's what we want. You can also map the land use as its own coverage. You could create a land use coverage, but we don't need to. It can read directly from the land use grid. Yeah. You have to have the hydrologic modeling module and then calculators. Compute GIS attributes. I created a video for myself a couple of years ago, back when I knew WMS really well, kind of like, I know I'm going to forget this in 6 months, but this is how you, from beginning to end, delineate a watershed. And I've got that video. I've watched it a couple of times because, I mean, you learn where a button is, and 6 months later, you don't remember which button to push or where it is. And so, I mean, as much as I like this program, and I feel like it's pretty intuitive, there's just so much going on. It's really easy to forget what you're supposed to be doing and where to click. All right, we need to import a map, because right now, it doesn't know what curve number to assign for all of these different land uses. These are the land uses in our area of interest. We've got some woody woodlands. We've got some deciduous forests. We've got some open water. And it says, well, the curve number for each one of those is 0. We're not going to get very good results if it thinks the curve number for each one of those is 0. So we're going to import that table that we downloaded before. It was that, so switch to all files. And the table that we want is that IWW, where is that? Curve number, there it is. All right, now that looks better. Now it's going to assign 98 for open water. If it's perennial ice and snow, I can't believe, oh, perennial. That's strange. I mean, I would think perennial ice and snow would be like a glacier. I'm surprised to see that there's anywhere designated as perennial ice and snow. Probably not a very big area. In a minute, we can look and see if there's any areas in our watershed that are perennial ice and snow. Okay, so import, and just one less glance to make sure everything's right. So it's calculating the curve number based on the soil type coverage and the land use grid. Click OK, and it's going to give us a report, and it needs to know where to save the report it's going to create. I'm going to put that in the same WMS folder that I've been working in here. Okay, so Morgantown soil CN report. Oh, no, that's not executable. I thought that was going to allow me to specify where to save it. I guess not. I'm just going to click OK. It brings up a little report. I guess at this point I can save it where I want it. Save as, I'll put it in that Morgantown CN report. So what it did is the same thing that when we were using the area of interest, you know, we had certain percentages of our area that were certain things. So here it's saying we've got 1,100 acres of deciduous forest, which is hydrologic soil group B. And so the curve number for that is 55, and it's doing a weighted average. You know, the curve number times the area, and then at the end, it's going to divide the total by the total area. And so my weighted curve number is 66.6. Yours is probably pretty close, maybe slightly different depending on where your outlet is. It should just automatically open after you do that calculator, compute GIS attributes. You just click OK and OK. Mine just pops right open automatically. Did yours not? Did everybody else's? Phooey. What's the default? Let's see, where did it save that folder, I wonder? Where did it save the report? App data, temp, WMS. I'm going to see if this is allowing me to change a different folder. No. Yeah, did you get it to come up now? Okay. Yeah, it looks like if you change the path, then it won't do that calculator, so you have to use the default path. I don't know if it was a problem you're facing. All right, so back to that report. That's not it. So it's saying our weighted curve number is 66. And if we had more of our watershed just in an urban area, of course it'd be higher than that. Do we have any of that perennial ice and snow? We don't. All right. Because we'd have to be really worried if it told us that some of our watershed was perennial ice and snow. But, you know, we've got a little, I mean, you always want to do kind of like a sanity check, you know, a reasonableness check. And in our case, I think it passes that. We've got a little bit of water. You know, we've got some forests, some crops. Okay. High intensity development. Some, you know, some pavement at a curve number of 94. All right, so now the nice thing about what it did is it took that curve number and it put it into HEC1 where it needs to know that. Let's open up the model parameters for HEC1. Now remember, the way that we did that with TR55 was we used the Select Basin tool, and you double click on the basin and it brings up a little menu where we're going to edit the parameters. Right now we just have one big watershed, one 4,400 acre watershed. And so the place where it put that curve number that we just calculated was into the loss method. We need to define a few things for HEC1 to work. First of all, you have to tell it about the precipitation. You have to tell it about what kind of a unit hydrograph to use. And then also you need to tell it how to calculate the amount of water that infiltrates versus runs off. And the way that's what loss method is. So for loss method, we want it to use the curve number that we just calculated and use the SCS method. But it'll also do the green amped if you wanted to go full out and, you know, use the green amped equation. You know, if you wanted to use the KSAT and percent impervious and so on. But we'll do the curve numbers for our loss method. We need to use the precipitation tool. Now, the most common thing for us to do here is basin average. Just assume that everywhere in our watershed has the same amount of rainfall, and we're going to go out and pick like the 10-year storm or the 20-year storm or whatever. You could do probable maximum precipitation, and that amount is along the lines of, remember when we did the NSS, National Streamflow Statistics? It had that one calculation that was just like way off the charts, crazy bananas, really high flow rate. The probable maximum precipitation is that same kind of, it's the most rain you could ever see in a place. It's not usually what you're designing culverts for. Maybe a dam, but not culverts. All right, so we'll do basin average, and the cool thing is it'll go and get the precipitation data from the web based on the latitude and the longitude. So it's interfacing with the precipitation frequency data server. So we're going to do a 24-hour duration, and let's just, for purposes of illustration, let's say a 10-year storm. You click Get Data. It takes just a moment, and now it's given us 3 values here. These 3 values are the mean. Well, it's a statistical model. The precipitation data frequency server, it doesn't just tell you what the rainfall is going to be, but there's a confidence interval, because all that data is statistically extrapolated from actual observations over time. And so for any given location, they have like kind of a good idea where 95% confidence that the precipitation is going to be between 3.7 and 3.2 over the course of a 10-year storm. And so if you're being really conservative and you want to say, well, we can't tolerate a very high risk of failure, so I'm going to use 3.71. And then I have 95% confidence that my culvert will be appropriately sized for a 10-year storm. So that's the interpretation of this upper and lower. But if you just click OK, it's going to, by default, copy over the mean value, 3.461. So I'll click OK, and there it is, 3.461. That's fine. We also have to define the series, because now it knows how much rain, but it doesn't know when during the 24-hour period that rain occurs. Like it doesn't know the temporal distribution of the rainfall. So if you click Define Series, then this is blank right now. You click on this selected curve, and we're going to do a Type 2 storm, because West Virginia is in regions for Type 2. Remember how we've looked at maps, and coastal areas have that storm that's pretty steady through the whole day, but a Type 2 storm says we have these peaks of intense rainfall where all at once, oftentimes an afternoon thunderstorm where there's been a lot of convection during the day and the hot air is rising and the condensation and so on. So what this is doing is it's saying what percent of the rainfall is happening at a certain time. So now we know the depth of rainfall and when it's happening. And so HEC1 is going to step through this storm in 15-minute increments and say, all right, how much precipitation was there during this 15-minute interval? How far did that rain travel over the surface? How much of that 15 minutes worth of rain infiltrated versus ran off? And so it does it in lots of little steps rather than kind of all at once assumption like TR55 did last week. TR55 last week, when we were typing the numbers into the window, it just automatically calculated the runoff depth. But this kind of has to do the calculation step by step in pieces. It's looking at the first time increment and then the next time increment and so on. So is everybody with me so far with the precipitation depth defined and the series defined? Oh, but you saved, right? You saved right before it crashed? Everybody's dropping like flies. This is like a World War II movie where all the bombers keep crashing, you know? Yeah, it's been about 10 minutes since I stopped doing anything useful. All right, so, okay. So we've got the precipitation. Now look at this. This is the work that WMS is saving us from. I think I mentioned before that in the olden days, back in the 70s, when HEC1 was developed as a model, people developed these models using text files. Like instead of using a nice graphical user interface like this, to set up a watershed model, you'd get out Notepad and count the number of spaces and type in some number, do more spaces. You'd have to just know where the data was supposed to go. And so what WMS is actually doing is it's creating a text file for us that then HEC1 is going to read the text file and output a hydrograph. And so that's why all of a sudden when I defined the precipitation, now this field has so much more data in it, because this is telling us how much rain there is in different time steps during the day. So a lot of these fields should be familiar, like precipitation averaged over the basin, 3.461. Well, we recognize that because that's our precipitation amount that we did. All right, so what have I defined so far? I've got my precipitation defined, the loss method. We need to define the unit hydrograph. Click on compute parameters based on the basin data, and we're going to use the SCS method. You'll notice that there's sure a lot of options available. Here's the lag time options, here's time of concentration, so lots of different equations. In our case, SCS may not be the best, but at least it's appropriate for the scale of watershed that we're using. Some of these methods are only valid for like 100-meter length. You know, like the Kerpich method is supposed to be applied over a relatively short distance. So we'd be outside the calibrated range for that. Now, the problem with what we're doing with the SCS method is our watershed slope's a little bit steeper than the SCS method was really intended for. And this watershed's not particularly steep by West Virginia standards. Do you see how it says 17%? I mean, what was the average slope of our area of interest from a couple of weeks ago? Do you remember that? It was like more than 35% slope. And so, you know, I've done research on some watersheds in West Virginia that are approaching 50% slope. So SCS method really falls apart when you're trying to do it with slopes like that. It'll be all right for tonight, just to illustrate. Okay, so calculated the lag time 1.82 hours using this little calculator tool, and then it filled that data in automatically here, which generates that same number being copied over into this text file that it's assembling. Here it is, UD, 1.8194. And so UD is the unit hydrograph method that's associated with the dimensionless SCS hydrograph. All right, so we are done. Now we can go to HEC-1, and I want to show you the job control. Job control is where you're saying the length of time that should be for each time step, and so by default it does it in 15-minute time increments, and it will do 100 15-minute time increments. So how many minutes are there in a day? 1,440. Come on, guys. How many seconds are in a day? 86,400. Acres in a square mile? That's feet in an acre. 640 acres in a square mile. You guys really need to bone up on your units. No, don't. It's useless. It's useless information. Huh? Yes. All right. So the reason I bring it up is that 100 ordinates at 15 minutes may not get our entire hydrograph. Your hydrograph may be truncated because that's only about one day. But when is the rainfall? The rainfall doesn't start to the middle of the day. If we go back to here and look at the precipitation distribution, it doesn't, this is one day. It doesn't even really start raining until 700 minutes. And so if you've got a small watershed, that's fine. It'll probably peak and empty during the 1,500 data points. But if you've got a big watershed, you may need to, in the job control, you may need to specify more than 100 ordinates. So, I mean, you know, electricity's cheap. We're not going to be adding too many computational cycles if we say 150. The only disadvantage of saying more is that then your hydrograph, you don't have as much view as you're showing it on the screen, but that's not really a good disadvantage. So just change it to 150. One other thing is you'd say, well, I want it to be super accurate. Maybe I'll do 1 minute computational interval. Things kind of fall apart if you get much less than 10 minutes. It's not good rounding. I did like some 5-minute computational steps, and I was comparing it to 10-minute, and I think like it was getting worse. It wasn't getting better. So I usually nowadays just leave it on 15-minute steps. I can't explain why. a smaller time increment gives worse results, but it does, and I think it's related to the way it rounds off precipitation amounts for such tiny little time steps. It's not able to do that with accuracy. So 15,150, click OK, and now save again. Mine hasn't crashed yet. I'm going to click Run Simulation. And it's asking where do we want to put this temporary output file. I'm going to create a special folder for that. Now it can't be too deep. For whatever reason, I've had problems in the past, like if it's in, you know, user, all users, you know, like if it's 5 or 6 or 10 subfolders deep, I've had the program crash because of that. So I try and have it as close to the root as possible, as close to the C drive as possible, but I think we could probably go one more layer and have this be HEC1 Output. Okay. Okay, so now it's saying it's, I don't see the whole location, but I'll assume it's there. Click OK. Once it goes, it ran, normal end, that's great. And here's my hydrograph. All that work, and we finally have our hydrograph. And it looks like it is getting me the entire drawdown of the peak because I did 150 rather than just 100. If I'd just done 100, then I wouldn't get to see this when it stops raining. All right, it's after 5. Let's take a break, and then when we get back together, what we're going to do is we're going to subdivide this watershed into smaller pieces and talk about routing. Any questions before we take the break? I hope you guys are loving this as much as I am. I think WMS is pretty cool. I think that HEC1 is awesome. You guys seem super enthusiastic, so that's good. All right, so we've got this hydrograph, right? Everybody have it? Good. Yeah, yeah, good. We can do the right click in the body of the hydrograph and have the same export options available to us as we did last week. You can export /print and then get the text /data and specify a location where you know, we could make this the Morgantown runoff txt, and then what we'd want to make sure to do is a table and points /subsets. I don't know why that isn't the default. Okay, export, and then once we get into that, here it is, Morgantown runoff. It's a text file that we could open up in Excel if we wanted to, and so the time is in minutes, and then the second column is flow rate in CFS. All right, so we can get at the hydrograph this way if we wanted to put it in Excel and do more calculations or graph multiple hydrographs at once, that sort of thing. If I remember how to do it, I want to show you another thing too that's pretty cool. Let's delete the hydrograph that we've got. So go here to hydrographs, delete all, or delete previous. We've only got one, so delete previous. Here in HEC1 is something called stochastic modeling. And who here knows about Monte Carlo? Has anyone here done some Monte Carlo? It's kind of like you introduce randomness into this model, and you want to see like what's the range of possible behaviors. So let's do 100 simulations, Monte Carlo, define the stochastic model, and we're going to add the variable. What we're going to do is we're worried, for instance, what if our curve number wasn't quite right? So what we're doing is we're saying let's have a minimum value, a maximum value, a start value, and then a normal distribution. Now everybody remembers what a normal distribution is, right? Bell curve. So what we're saying here is that what if we had as our minimum 60, our maximum 90, at the center of the bell curve is 75. Well, what was our curve number originally was what? 66. So let's put that at the center of our bell curve. So the start value, we'll change that to 66. Okay, and we'll go from 60 to, so if we went down 6, then we'll go up 6. So we'll go to 72. 66 plus 6 is 72, right? 72. So what it'll do now is if you scroll sideways, we're going to do 100 runs of HEC1. And it is going to do a run for lots of different curve numbers. Each one of these runs will just have a different curve number. But the frequency, most of these curve numbers are about 66, but some of them are on the high end, some of them are on the low end. And let's click OK. And this is where I hope, fingers crossed, it'll work. Run stochastic model, and just OK. I think it's buried too much. Let's see. HEC1, I'm going to run stochastic modeling. Did yours work? Is it clicking away? Doing lots of stuff? So it hasn't crashed yet, in other words. All right, so Monty, let me see if I can do it in here, and maybe it won't crash this time. So I'm just closer to C. All right, so OK. All right, so HEC1, run stochastic model. Now see, I'm not even getting the option. Oh, maybe. Oh, it's running. All right. So see what it's doing? It's running HEC1 over and over again. All right. So I think that error message I just got was because the default folder, yours is going, the folder location was too many folders deep. And so if you just browse to another location, no? Uh-huh. Yours may not have the curve number specified. Did you know how we did that stuff about adding a variable? You can cancel yours, because I think you're right that it's not doing anything good. So try stochastic modeling, and the one above it, and what location are you putting it in? Okay, save that somewhere else. Just do it like C temp. Create like a folder in, and create another folder. Yeah, put it in there. And now try running it. All right, it's going. Show him how to do that too, okay? I think yours isn't running, and it won't let you quit. You just gotta wait. Okay, 97. What's mine on? 92. Maybe we should have done 50. 100's kind of a lot, right? Let me pull open my hydrographs, because I think what it's going to show is the distribution of hydrographs. That's what it should. But once you close this, let's look at the Monty. All right, yeah, here's the solution for each one of those. I thought it would automatically read the solution and show a bunch of hydrographs. That's what I've gotten before. That's a little bit disappointing. I'm going to delete the previous. Yeah, let me go back to, okay, so stochastic modeling, you add the variable, and then by default, I think it was centering it on 75. So you change the start value to 66, and this time I'm just going to do 10 simulations. It'll be faster. Okay. Run. Yeah, change it to 10. 10 will be plenty. Hopefully I'll be able to pull open the hydrograph and see all 10 of them with the spectrum of outputs. Well, they're all on top of each other. It doesn't seem to actually be changing the curve number. Okay. No, I think I just remembered something. Okay. It's all coming back to me. Go back into, so it's the curve number. Yeah. Stochastic modeling. Okay, see this key -1 for curve number? We have to go back into our model, and in the place where curve number would be, see where it says 66.6? I think what we need to do is put a -1 in there. I think. All right, so -1, and now stochastic modeling. Yeah, that's good. Run stochastic model. So I think I need to put that flag of -1 so that it would know what to do. Now, fingers crossed that now I got a good looking hydrograph with all the many different. Yeah, all right, there it is, just what I wanted to see. So that's kind of like the envelope of possibilities. Yeah, so let me demonstrate that again. Boy, the heater is on in here. I was just commenting about how weird this building is. So let me show you where you needed to put that -1 in. Okay, so I'm going to delete these hydrographs. Okay, open up your watershed model and go to loss method. And you need to change the curve number that had been calculated by that little tool we did. Remember, we did the calculator and it said 66. Change it to -1. And if you change it to -1, then it'll know to look at the Monte Carlo file for what curve number it should be using for each run. So the reason we kept getting the same runoff hydrograph is because there was no difference in curve number. But if we tell it -1, then it knows to look elsewhere for the curve number for that run. All right. Now, you can do a Monte Carlo on more than just a difference in curve number. You can also set up precipitation variation. So that's another thing where there's a lot of uncertainty. So we're never quite sure if we've got the right curve number. We're also never quite sure if we've got the right precipitation. Do you remember what was the range of precipitations? If we go back here into our precipitation from the web for our, we've been doing 10-year storms, I think. Get data. The range was I'm going to write this range down because I want to do a Monte Carlo. 3.233 all the way up to 3.709. All right, so now let's do both. Let's do, I'm going to have to put in a flag there too for my precipitation amount. Change the average precipitation to -2. I've never actually done this. I hope it works. All right, So we've got -1 for our curve number and -2 for precipitation. And then we're going to go into the Stochastic Modeling tab. We've already got the curve number. Let's do 20 simulations. It'll be more fun. Twice as much. Okay, so we've got -1 for curve number, add variable. We'll do -2 for precipitation. So it knows it should go get different precipitation data. And then the starting point would be, I just have the range. Our minimum is 3.233. Our maximum is 3.709. Does anybody remember what our starting, like the midpoint rain was? 3.4. Yeah, that sounds good. All right, so now let's scroll sideways and make sure that it's distributed that in a reasonable way. So what it's going to have is it's going to have one run with the curve number of 69 and the precipitation amount of this. And it's going to have like all these different combinations. And you could override it if you wanted to have like run 20 be one where that's like, what if it was 74 and so high curve number, and what if it was 3.709? So you can overwrite those. You don't have to use the automatic distribution. So that would be like our really rainy and high curve number, worst case scenario. Here would be our best case scenario, like this is the one where we want it to be 66 and hardly any rain. So this one would be 3.233. All right, so we've got that. Fingers crossed that it will run this model. So I've never done both a -1 and a -2. Just guessing. So it's kind of miraculous if you think each one of the times it clicks through, it's done 1,500. It's calculated the watershed model in 1,500 pieces from beginning to end. It's looked at how much precipitation occurred during that 15-minute increment, how much of that precipitation ran off versus infiltrated, how quickly the water's moving through the watershed. Hey, that turned out really good. So here's our best case scenario. Here's our worst case scenario. And if we right click and download that data, text file, we can go to for Excel, Monty, TXT. Table, columns. And so now it's got, for each one of those 20 runs, the time and runoff. And so you could create your own set of hydrographs that are formatted differently than this figure. Did everyone get Monte Carlo to run at least once? How many of you got the 2-parameter Monte Carlo to work with both precipitation and curve number? It's going. You set it to 100 just for super fun, right? Did you really? Yeah. Okay. Well, it'll be done in a while. Did you get it to work? But it's all the same. So let me show you. Go into the watershed model. Use that one. Yep, double click. Change loss method. Curve number -1. Okay. Done. HEC1. Yes. Okay. All right. Delete this one. Delete this variable. Yeah. Or if you want to, you can change it to precipitation. Yeah, so change its curve number, say, make it say precipitation. And then change these, the precipitation amount, like do 3.2 for minimum, maximum 3.7, 3.2 minimum, yeah. And then for start, do 3.4. Okay. Now also open up the basin again because we have to put the -2 flag in for precipitation. So here, make it -2. Okay. Done. How many did you do? 10. Okay, good. Hopefully, when this is finished, then there will be many different hydrographs, not all on top of each other, but should be looking more different. Yes, perfect. Good. So that's something that I did. I learned that tool not for uncertainty analysis, but because I needed to do a 2-year storm, a 5-year storm, a 10, 25, 50, 100, 200, and 500. So I had to do 8 different simulations for 15 different watersheds. And the thought of running each one of them individually drove me crazy. So I was using stochastic modeling just to, it's like batch execution. You can run your watershed model in batch, and then you don't have to do it manually each time. So it's kind of a nice tool. Any questions about that? The last thing I'm going to show you tonight is subdividing watersheds. So let's delete all of our previous hydrographs, and we're going to break this up into a second piece. So go into the drainage module, and we're going to drop another outlet. Break this up into pieces. There's a couple of ways to do it. If you go into the delineate basins, that's not what I wanted to do. Okay, go into the hydrologic modeling wizard, delineate watershed. If you click subdivide watershed, like if you said what your maximum area is, then it'll break the watershed up into pieces, like as many as you need. Like if you say, I can only have a maximum, we'll do that in a minute. For now, we're going to manually drop in another outlet. Let's say that we want this branch. Somehow we suspect that this branch is different than the rest of the watershed. Maybe it happens to have particularly low curve numbers or something. So what we could do is drop another outlet there and then delineate the watershed. And what it's going to do, we've got two outlets, and it's going to calculate the characteristics of both of them. So we've got the main one and then this other sub-basin. Now the curve number is 0. We have to go through the calculator again to have it calculate the curve number for us. So it was here in calculators that we did compute GIS attributes, coverage, grid, everything's fine, okay. It'll give us that same little report. I hope. It's calculated our curve number, 66.5 for that one. This one has a curve number of, oh, stupid labels in the way. If I go over here, I can select the watershed, and it'll tell me its characteristics over here. So this curve number is 67. It turns out that both of these watersheds are pretty close, but 67 and 66, it's slightly different. But what we could do now is we can set up HEC1 to run again. So we go here into the hydrologic modeling module and double click on select one of the basins. And we have to do the same thing that we did before. We have to go through and identify the precipitation. We're going to use the basin average, get the data from the web. We'll do the 10-year storm, get data. Now remember the 3.461, okay, because I'm going to type that in manually for the next one. But I have to define the series just as before, like type 2 storm, 3.461. I'm going to remember that. Loss method, it automatically copies over the curve number that it calculated. Unit hydrograph, I have to have it calculate based on the basin data. I'm going to do the SCS method. And it knows all the parameters for this new watershed subbasin. It has a new watershed length, a different slope. Okay. Now see here where it says next station? You can either close this and then open up the other one manually, or you can cycle through them using these arrows. So the first one I did was the main big one, and I typed in some of the information for it. Now I'm going to do the little one. And so you'll notice here in the output window, there's nothing defined yet. So that's how I can tell I'm on the right one. If I go to the previous station, now what we're looking at right now, it doesn't have any of the basin data, because right now we're looking at one of the reaches, which is a stream. We can actually tell it some information about the stream that connects the two outlets together. Because here, this outlet is upstream of the other one. So you see this blue line here? That represents a river. That blue line, I can turn off the contour lines. That makes it a little bit more obvious to see. This blue line is a reach that I could I'll just bring it up this way. Connecting 3C and 4C. And so, okay, so I'm on the basin I've already told it information about. Let's go into the other one. So precipitation, basin average, what was it, 3.4 something? Get precipitation from web, I guess. 10-year data, get data, 3.453. Define series. You got to tell it the temporal distribution. Okay. Loss method, the curve numbers carried over from that calculation that we did a minute ago. Unit hydrograph, we have to specify using basin data. Change it to the SCS method, 0.92 hours. Okay. All right. Now, let's see if I can get to that reach, the one that connects 4C and 3C. I think this is the one. So if you click on routing data and change it to one of these methods like kinematic wave, what it knows is it knows the length of that reach. And so that river is 1,400 feet long. And here's the slope of it. It's 0.6% slope. What do you think N is? It's not filled anything in for N. What we're doing right now is trying to model a river, because what it's going to do is it's going to account for the travel delay. You know, there's a hydrograph that's discharging from the upstream outlet and it's going in a river. So it's sort of like you're dumping a hydrograph into a river, and that causes the hydrograph to spread out a little bit. It dissipates the peak of the hydrograph because of routing. And so what we're adding here is information about the river that the water is going to be traveling through. So what do you think N represents? Think back to hydraulics when N was a really important letter. Yeah, it's Manning's N. It's the friction coefficient. So do you remember like 0.013 is a typical N value for concrete? Like a typical channel N, you know, maybe if it's relatively smooth, we could do 0.025. Would maybe be a typical natural channel doesn't have a lot of like jagged rocks or something. But it also needs to know a little bit of information about the shape of the channel in order to calculate how deep the water flow is going to be and what velocity can be achieved through the channel. And so, you know, if you've been into the field, you may know that, oh, the stream is about 15 feet wide, and the side slopes for a trapezoidal channel, it has about 2-to-1 side slopes, so Z is 2. And what it would do with that is it's going to calculate lag times inside of the channel. It's just a way of combining the hydrographs together. Okay, so I'm done. I've defined everything that we need for both of the basins, and the reach is also defined. So I'm going to click HEC1, run simulation. Okay, we're just doing the single simulation this time. We're not doing 100 of them. It pops open with our hydrographs. Now look at this. There's a hydrograph for the watershed and for the outlet, and the two are identical. So this 204, time to peak 780. And if I open this, 204, 780. So the outlet hydrograph and the watershed hydrograph are the same when you haven't done any routing yet. But there's also the effect of the hydrograph as it's traveling through the reach. So this one had a peak of 204. Well, inside of the reach, the peak is 201 because the reach is kind of, it's hard to explain. They call it routing the flow when the flow peak is dissipated and it's spreading out the width of it as well. And there's a delay there. So here is the hydrograph just of our bigger subbasin, but then this is the combined hydrograph. This has both of the basins together. So this peak was 605. This peak was 204. So what's 605 plus 204? 605, 204, 809. All right, so is that true? Is that what we get down here at the combined one? No. Why do you suppose that it's not just simply the addition of those two peaks? They're coming in different waves, right? Yeah, very good. So look at the time to peak. This one was at 780 minutes. This one is at 840 minutes. And so, you know, I think you get my point. You know, it's like one of them is here, then the other one's coming on top of it, kind of like a little more there. And so the combined peak is going to be later. And it also has the effect of the routing there as well. So let's do one last thing before we finish for tonight. Let's delete that. Let's try that one where we let it automatically delineate however many watersheds we need based on like a maximum area. So if we go to HEC1, no. It was in here, in the drainage module. We go into the hydrologic modeling wizard, delineate watershed, and our maximum area is going to be, I think overall, wasn't it about 4,500 acres? So let's say that we can be 1,000 acres each. We want no watershed more than 1,000 acres. Subdivide watershed. Okay. I'm going to select this one to subdivide. It's thinking. Sometimes it picks kind of screwy places to put them. Oh man, there's lots. I said 1,000 was the maximum, right? Did I accidentally type 100? No. That's bizarre that it's broken them up into such tiny little pieces. Huh. Interesting. Well, I've used that tool in the past and got pretty good results with it, but this time it was just kind of bananas. But I wonder if I saved my work. I'm gonna do new. Oh, I just open up this. It'll open up my, okay. No, all those are still there. think I saved my work after doing that redelineation. Okay, yeah, here I've just got a single one. I'm going to try and delineate it better this time. Okay, so it didn't pick good spots, in other words. Maybe it's best that you drop the outlets yourself to make sure that it subdivides it well. Maximum area. 2,000 acres. Do it. I wish it had a minimum as well. Man, why so many? Well, that's interesting. Anyways, I feel like you have what you need to know to be able to do the next homework assignment. We've covered a lot of ground today. We've learned how to go and get the soil type data, load it into WMS, clipping it and putting it in the soil coverage, automatically getting the land use data, calculating the curve numbers. You learned how to run the model, get the rainfall data, and even how to do the stochastic modeling if you ever have an opportunity to consider the range of possibilities rather than just the middle value. If you want to know the best case, the worst case, when you're facing uncertainty, then the stochastic modeling can be useful for that. Any questions before we call it a night? All right, well, the only thing on your plate right now is the homework assignment that's due next week is to pick a watershed and do this for that watershed. And in fact, I think it would be interesting for you to do the stochastic model as well. It's not like brain surgery or anything. One thing I'll point out is that I'd like you to include some written discussion of, the watershed that you have selected, why it's a watershed of interest for you, some descriptive text that explains what you did in the steps. And what I want this to be is a guide for you to remember how to do these same steps in the future. So if it's only screenshots with no accompanying description, then that won't be as useful to you in the future as kind of like if you're creating a tutorial for yourself on how to create a HEC-1 model. So that's what I intend really homework 12 to be, is you writing a tutorial for yourself so that in 6 months that you know how to do this. Yeah.
Not the same task, but we create a tutorial, right?
I wasn't as articulate with homework 11. I didn't come right out and say it's a tutorial. It's the same kind of idea, but in some cases people just submitted like pictures. And so I'm trying to make it clear that the pictures are a big part of it, but I'd also like you to explain step by step what the process is. Not just proof that you did something, but also instructionally something that you could follow in the future. All right, so next week we're going to be done with WMS. You don't need to bring your computer next week. Say goodbye to WMS after this week. We're going to be talking about flood zone management, and then in our last lecture we're going to be talking about subsurface hydrology, so things like groundwater wells. So I will see you next Wednesday, and feel free to let me know if you've got any questions.